This video is meant as a quick introduction to the chain rule. An alternate title for this video could be How to Take the Derivative of a Composite Function. We're going to state the chain rule. We're not going to prove the chain rule, but we will look at several examples. We'll start with a problem that you could have seen in algebra classes years ago. Suppose a car is cruising down the highway and it has some sort of fuel efficiency. Let's imagine that it burns 1/35 of a gallon of gasoline per mile. Let's also suppose that the car is going at a constant velocity of 70 miles per hour. One question you could ask is, at what rate does the car consume fuel? It's pretty clear in this case that if we just take the product of these two rates, which by the way gives us the number 2, we'll get the rate of consumption of fuel. If you analyze the units, you'll notice that the miles cancel, and in fact we get 2 gallons per hour. The motto we might invoke here is that rates can be multiplied. Now that's a pretty wishy-washy statement. It doesn't really say anything because you can multiply any two numbers you want together. But it's a shorthand way of saying when you take two rates and multiply them together, you're going to get a new rate. And in fact, if you just analyze the units, you might be able to discern what that rate is telling you. But the general principle here is that to obtain new rates, it's possible to multiply rates together. So let's look at a fairly sophisticated example. Suppose you have a weather balloon that you release and it rises up through the atmosphere, and you could keep track of the altitude, you could keep track of the time, you could keep track of the pressure if you have a barometer on the weather balloon. So we'll measure altitude in kilometers, time in hours, and the units of pressure, one common unit of pressure is the atmosphere. The atmosphere is a unit that's designed so that at sea level the pressure is 1 atmosphere, and then as you go up the pressure decreases. So what we're going to do is ask the question, at what rate does pressure change with respect to time? So we need to have more information before we can really get at this problem. We know that the pressure decreases exponentially as a function of the altitude. And in fact, if you measure pressure in atmospheres and altitude in kilometers, the formula for this is roughly P equals 0.867 raised to the y. And let's suppose that the balloon rises in such a way that its height is a cubic function of time. So if we're measuring the altitude in kilometers and the time in hours, let's suppose that the altitude is given as negative 20t cubed plus 60t squared. Taking a step back, we'll notice that p is a function of y, and in turn, y is a function of t. Putting these together, you realize p is a function of t, and this is an example of what we call composition in pre-calculus. You're taking the output of one function and inserting it as the input of another function. Now in this case, the output of your altitude function can be plugged directly into the input of the pressure function, and you get an explicit formula for p in terms of t. We'll notice that this is not a simple exponential function. It's not a constant raised to a variable. And it's not a polynomial function either. And it's really not even a simple sum or product or difference of these kinds of functions. So at this stage, we're stumped by this question of what dp dt is. The way to get unstuck is to apply the chain rule. The chain rule is the way for generally taking derivatives of composite functions. So let's make our question even more focused. Let's ask, at what rate does pressure change with respect to time when t equals 1. So we have in mind a very particular moment. We want to find the rate at which pressure changes with respect to t. Even though we can't take the derivative of the composite directly, we do know how to take the derivative of each function individually. The left-hand function is a pure exponential function and the right-hand function is a polynomial. So finding these derivatives is no problem. Now we have this notion that rates should be multiplied together. So if we want dp dt, we might expect this quantity to be the product of dp dy and dy dt. But there is a critical question we have to ask. Which rates are we going to use? We'll point out that dp dy, the rate of change of pressure with respect to altitude, is not constant. It changes as a function of y. Similarly, dy dt, the rate at which altitude changes with respect to time, is also not a constant. It changes as a function of time t. So let's analyze the rate of change when t equals 1. It's pretty clear that we'll want t equals 1 in the right-hand derivative. This will give us the rate of change of altitude with respect to time for the balloon at t equals 1. That much is pretty obvious. For dp dy, we need to know the correct y to use. But we can easily figure this out. The observation is that when t equals 1, y equals 40. So it's really when y equals 40, that's where we should be concerned about. So we can plug y equals 40 into the left side and t equals 1 into the right side, and we will have the appropriate rates of change, which we can then multiply together to get dp dt when t equals 1. In this case, we get about negative 0.028 atmospheres per hour. So let's use the calculator to check our work. We've just calculated dp dt when t equals 1. Our goal here is to put the explicit formula for our function into the calculator and then use the calculator's ability to calculate a numerical derivative to check our work. So here's a graph of the function, and you can see that the pressure decreases as a function of time. And then we're going to use the n-derive feature. And just recall that n-derive calculates a secant slope over a tiny interval. It's the calculator's way of approximating a tangent slope. And in this case, the calculator yields the following quantity, which is pretty darn close. It's not going to be exact because it's calculating a secant slope, but it's certainly close enough to give us confidence that we've got the right answer. So let's revisit our problem with a little more generality. Let's assume that we just have functions f and g, and that our composite is f of y, which in turn is g of t. And to be even more explicit about it, we can say this is p of t. Here's our composition. And we want to find the derivative. We expect dp dt to be the product of dp dy and dy dt because we expect rates to multiply. So what we're going to do is simply swap out the Leibniz notation for functional notation. If you're just careful about this and literally swap out the right pieces, it's not too bad. So for instance, dp dt we could simply write as p prime of t. Similarly, dy dt could be written as g prime of t. And of course, dp dy could be written as f prime of y. But you'll notice one of these things doesn't belong. We've got the left and right hand functions expressed as functions of t, and the middle function expressed as a function of y. But we can fix this because y equals g of t. So if we substitute that in, we get dp dy equals f prime of g of t. Now we can reassemble all the pieces. Our product then looks like this. This is the chain rule expressed in functional notation. If p of t is the composition f of g of t, then p prime of t is f prime of g of t times g prime of t. Let's have a go at the chain rule one more time. We'll start with the composite function f of g of x and ask what is the derivative with respect to x of this function. Using the principle that rates should multiply, we know that it's a derivative of f times the derivative of g. But where are we going to evaluate these functions? The so-called inner function g sees the argument x first, so this is the easiest call. We should evaluate g prime of x. But what does f see? F sees the output of g, so when we evaluate f prime, we had better evaluate it at g of x. This statement of the chain rule is quite handy when you take derivatives of various functions you meet. So here are the relevant functions that describe pressure as a function of altitude and altitude as a function of time. And here is our explicit composite. Here are the relevant derivatives. We know how to take the derivative of an exponential function, and we know how to take the derivative of a polynomial. The chain rule tells us how to take the product of these derivatives evaluated at the right spot. And when all the dust settles, you get this fearsome looking expression. So as bad as this looks, it does have the virtue of telling us explicitly what the rate of change of pressure is with respect to time as a function of t and t alone. If we return to our original question, which is what is the rate of change of pressure with respect to time when t equals 1, we can simply substitute 1 into this expression. And you'll notice that if t equals 1, this exponent is 40 and this expression is 60. And so p prime of 1 is equal to this expression, which hopefully you'll notice this as dp dy when y is 40, which we calculated earlier, and this is dy dt when t equals 1. And so we've recovered the original rate we found earlier.